Saturday Morning Physics is sponsored by the University of Michigan Department of Physics and by gifts from friends of the program. Local broadcast is made possible by Pfizer Incorporated.
So I told you about gravitational waves, where they come from, and also told you why we think they're so incredibly difficult to detect. But today I'm going to tell you why we think we can detect them anyway. I'm going to tell you in some detail about two different types of detectors that are used to detect gravitational waves, suspended bars and interferometers. And I'm going to talk in some detail about something called LIGO, which is the Laser Interferometric Gravitational Wave Observatory, a project that I'm involved in that looks for gravitational waves. And I'll show you some results of searches to date. You haven't heard about them in the New York Times, so you know that the search has been unsuccessful, but I'll tell you about them anyway. And then what's more interesting, I'll tell you the future prospects for real discovery. Okay, so for those of you who didn't attend last week's lecture and those of you who may not have absorbed everything I told you last week, let me review some of the basics of gravitational waves. We know that space and matter interact with each other. Matter makes space curve, and the curvature of space affects the way matter moves. And for example, in this so-called rubber sheet model of space, we have a large object creating a depression. This is a two-dimensional model of a three-dimensional space. We have a heavy mass that warps the surface, and the other mass is affected by that warping. It's attracted to that depression. And in fact, when it falls into the depression, it deepens the depression. Well, an extreme example of that would be two neutron stars orbiting each other in a very tight radius, a small radius of that orbit, and rapidly orbiting so that they generate these ripples in space. These are gravitational waves, and if these waves are strong enough, we may be able to detect them even though we may be millions or even billions of light years away. So we say that gravitational waves are ripples in space, or ripples in the space-time fabric. These perturbations propagate in a way that's very similar to light. They travel at the same speed, at least we think they do, and they have two independent polarizations, just like we have for electromagnetic waves that make up light. And let me just remind you of the example I showed you last time. Here we have a gravitational wave impinging upon a ring of test masses. You can imagine floating out in outer space, strung together like beads on a string, for example. These masses are going to get stretched apart during part of the passage of this wave, while the beads are compressed together in the perpendicular direction. So vertically they're stretched, horizontally they are compressed. And if you wait half a period of that wave later, you see the opposite pattern. We have stretching horizontally and compression vertically. That's one passage of a gravitational wave, one period of a wave. If you take that same pattern and you rotate it 45 degrees, as shown in the bottom diagram, you get the other independent polarization of the gravitational wave. Now, we measure the strength of a gravitational wave in terms of a fractional change in distance, that is a strain. We don't denote it by h typically, small h. And what it tells you is that the change in distance between two test masses, or say floating out in space, is equal to the strain h times the nominal distance between them, the distance they had before the gravitational wave came by. Here's a cute graduate student depiction of this process, exaggerated by many orders of magnitude, that shows a nominal distance L and a change in this ring of masses, this delta L. And the ratio delta L over L is the strain. If we have a gravitational wave detector, we might be able to hope to see a gravitational wave that looks something like this. This is what's known as a chirp from the last 9 seconds, in this case, of an in-spiraling neutron star binary system. I'll play what it sounds like for you. If the wave amplitudes were large, it would actually be easy. It would look something like this. Well, okay, maybe I should have gotten a graduate student to do this for me, but anyway, animation leaves something to be desired. But the problem is that we don't expect distortions of that scale. We expect distortions of the scale of 10 to the minus 21. Okay, so the question is, how in the world can we possibly measure something like that? Now, several methods have been tried over the years to detect gravitational waves directly, At low frequencies, one can monitor signals from spacecraft. They're going, for example, out of our solar system and look at them over long periods of time. Look for modulations in those signals. You can also look at distant pulsars, which I talked about last week, which have these very periodic signals coming at us all the time. If you look at an array of those all over the sky, you might hope to see a little bit of a disturbance of the timing of those pulsars with respect to each other. But what I'm going to talk about today are terrestrial experiments, where we try to detect the waves right here on Earth. And there are basically two different techniques that have been tried for this detection. One is to look at the energy that is deposited in a suspended bar, resonant bar, and the other is to look for a disturbance of a laser interferometer. Let me first talk about the bars. If you imagine having a cylindrical bar, metal bar, aluminum alloy, for example, that is suspended from a wire so that it's somewhat isolated from its surroundings. I'll talk more about that issue in a moment. Then if a gravitational wave comes by, it can disturb the bar. It will stretch the bar and compress it. Gravitational wave affects both matter and space. It will stretch it, and it will leave energy in that bar. If you place a piezoelectric transducer at the center of this bar, a piezoelectric transducer is something that converts strain into an electrical signal. Oops, I'm in a bad spot in the auditorium, getting a little bit of feedback. Then you can generate an electrical signal that measures how much this bar is getting stretched or compressed by the passage of a gravitational wave. There's a mass spring analog. Imagine two masses attached by a spring. A gravitational wave comes along, it pulls the masses apart and lets them go. They'll just oscillate for a while afterward. In some sense, one is ringing a bell. Let me demonstrate that you can do this sort of thing with an ordinary bar. This is an aluminum bar that's not so different except in its size from the kind of detectors that have been used to look for gravitational waves. What I'm going to do is basically stroke the bar and try to generate a longitudinal vibration in the bar that's analogous to what a gravitational wave would do. This is the trickiest demonstration. It doesn't always work, but I'll try. Okay, I'll relieve your ears. That is a singing rod. And we would not expect a gravitational wave to do something that dramatic. We expect a much smaller excitation of that resonant vibration, but we would like to be able to see something like that with a gravitational wave passage. Okay, now many suspended bars have been built over the decades, since the 1960s. Joe Weber founded this whole field of gravitational wave detection by building such bars and looking for their vibrations. This photograph shows him several decades ago with one of the original bars. It's a big aluminum bar. It's suspended by a couple of cables. If you look closely, you can see these little rectangles. Those are piezoelectric transducers, which he was using to try to read out the signal from the gravitational waves that might have passed by. Now, one problem with these bars is that they're inherently narrow band. They can only detect the energy from a gravitational wave if it happens to be right at their resonant frequency, within, say, a hertz or two of that resonant frequency. And we're looking for gravitational waves that have a more complicated spectrum to them, sort of things I showed you last week. So they're not well suited to reconstructing chirps like the one I just showed you. However, it has been seriously proposed that one could build a xylophone of these different bars of different lengths and masses and so on. And just to illustrate that, here's a xylophone. So here's one bar at one frequency. So if you had an array of those sitting next to each other, you might well be able to infer more about the gravitational wave chirp than you can from a single bar. And that has been proposed. I don't know of anyone in the world who has been funded to build one of those because each bar is quite expensive, but it is a serious proposal. Now, let me show you some photographs of bars that have been built over the years. There are several operating in the world right now. The modern bars are operated at very low temperatures to reduce the thermal noise that would fool you into thinking you had a gravitational wave. And so they have to be put inside these giant cryostats. So there's an elaborate cottage industry that's based on building these sorts of bars. But now let me talk about what I think is a better gravitational wave detector, namely a suspended interferometer. But first let me address what an interferometer is. Recall from last week that if you have two waves that are synchronized so that their crests overlap with each other and their troughs overlap, you end up with a wave that is twice as big as either one of the original waves. If you desynchronize them slightly, so the crests don't quite overlap with each other, you get a wave that's bigger but not as not twice as big. And if you desynchronize them completely, so that they're half of a wavelength apart, then you get complete destructive interference. And this sort of effect can be exploited with an interferometer. Let me illustrate that with an audio interferometer. Last week, I turned on an audio interferometer made of 2 speakers that are coherently driven with the same tone. I'm going to do that again. There's one difference. Last week, I asked you to plug up one ear and move your head around, and you could hear an interference pattern as you did that. Today, what I want you to do is keep your heads fixed. And what I'm going to do is move one of the speakers around. So it's an interferometer. This allows me to measure indirectly the distance between these 2 speakers. If I were sitting out in the audience and did my calculations right, I could tell you the distance between these speakers, at least a change in the distance, just by listening to that pattern. And the interferometers that look for gravitational waves are based on the same principle. Let me illustrate that. We use a Michelson interferometer. You may have heard of the Michelson-Morley experiment, which is one of the founding experiments in the field of gravitational physics that showed that the speed of light is independent of the direction in which one looks and independent of the velocity of whatever is producing that light. I'm going to talk about a simpler version of that experiment here, namely an ordinary Michelson interferometer. You have a coherent light source, in fact a laser in our case, that shines on what's called a beam splitter. In this case, it's a semi-silvered mirror. Half the light goes through the mirror this way, and half the light gets reflected that way. In each case, the light goes down to another mirror, which is 100% reflective, and the light bounces back. Now, when the light comes back from this mirror and from that mirror, it combines together. If the waves are synchronized, as I showed you a moment ago, you get constructive interference, and you get a bright light here at your light detector. This could be a photodiode or a photoelectric cell, sort of thing you have in your garage. Or the waves could be out of synchronization. They could be half a wavelength apart, in which case you get complete destructive interference, and you see darkness here. Okay. Well, we have such a Michelson interferometer right here on this table, and I'm going to project the image onto this monitor, like so. This is looking at the output. This is looking essentially at that light detector, showing you the fringe pattern. These are crests and troughs of a wave that depend on where you're looking on the screen. And if I simply touch this Michelson interferometer just a tad, I can make that pattern change. Now, every time you see one of those fringes go through itself, say going through the center, that means you're moving a small fraction of a micron, a small fraction of a millionth of a meter. So this turned out to be an extremely sensitive distance measurement. I can measure easily, with this very simple gadget, I can measure things with a precision of probably 10 nanometers or better, if I had a very well-calibrated photodetector. It's a very simple gadget. So this is a basic idea of a gravitational wave detector. If a gravitational wave passes through a device like this, it makes the distance between the arms stretch or compress, and a Michelson interferometer detects that beautifully. I think I'll just leave that up. So the interference at the detector depends on the difference in lengths of these 2 arms, which is the difference that matters, not the absolute distance. And I just gave you the demonstration, and oops, sorry. A gravitational wave will cause the same length difference, except it's been highly magnified here, again by a graduate student who has more animation skills than I have. Okay, now, why would we want to suspend our interferometer? Okay. Well, suspended mirrors are in near horizontal free fall, we call it. That means that if they're swinging this way, and actually we want them to be at rest, but they're free to swing this way, that means they're free to move in this direction. They're free to respond to the presence of a gravitational wave. But in some sense, what's more important is that that isolates us from the ground motion. So let me illustrate that here with a simple pendulum that's being driven at the top. So here is the support of our pendulum, and I can change the frequency at which that pendulum is driven. This gadget was originally built to demonstrate resonance, to show that if you have a resonant frequency, in this case it's a little bit less than 1 hertz, once per second, then you get an amplification. This pendulum bob rings the bell because there's an amplification of the small motion you see up here by the fact that we have a frequency of the bob motion that agrees with the frequency that I'm driving it at. But what's actually more important for gravitational wave interferometers is what happens if I go to higher frequencies, if I go to the kind of frequencies I hope to see with a gravitational wave detector. If I increase the frequency of the driver, you see I have actually a relatively large amplitude at the top, but the pendulum is not responding at a large amplitude. I get a demagnification. I'm getting a suppression of that oscillation just by the very fact that I have a pendulum. Now this is not a very high frequency, a few hertz, but the gravitational waves we care about are 100 hertz or higher. That means, well, the suppression goes like the inverse square of the frequency of the vibration. That means that at 100 hertz, we have 10,000 times better suppression of external disturbances with a pendulum than we have at 1 hertz. Okay? So that's the primary reason that these things are suspended, and that's true both for the interferometers and for these resonant bars. You want to isolate them from their environment. Now, interferometers have a broadband response, typically in the range 10 hertz up to a few kilohertz, and that means that they are, unlike the bars, well suited to measuring a chirp like this, to allow you to reconstruct that waveform unambiguously. And the bigger your L is, the bigger the arms that you have, the more precise your measurement of the strain will be, the ratio of the change of the length divided by the length. Okay. But you might still be skeptical. I mean, can one really measure delta L over L to a precision of 10 to the minus 21? Well, let's go through some numbers. Let's imagine we have a relatively simple gadget, a 1-watt laser, and let's just pick an infrared laser whose wavelength is about 1 micron. And imagine that we have an interferometer that's 1 meter long. Now, it turns out that 1 watt of light corresponds to 5 times 10 to the 18 photons per second. Recall that electromagnetic waves are both particles and waves simultaneously. We could spend a whole lecture talking about that issue. But in any case, what we measure in our photodetectors are actually photons, one at a time. And with 5 times 10 to the 18 per second, we actually have a very small fractional error on the number, fractional fluctuation on the number of photons that hit that photodetector at any given time. If you imagine measuring the period, half the period of a 1 kilohertz wave, the number of photons that hit the photodetector during that time corresponds to a fractional fluctuation, a fractional measure of the light intensity at the level of 10 to the minus 8. Now, there may be other noise sources in your experimental apparatus that degrade that fundamental limit, but in principle, you can get down to 10 to the minus 8 for the precision with which you can measure the intensity of the light. Now, that intensity fluctuation is related to the ratio of the change in length of the arm over the wavelength of the light. I just illustrated that with this experiment. The fact that when I pushed on one arm and changed the length slightly, the fact that I was able to see that was because I had a very small wavelength. This essentially magnifies the effect of a small change in length. So if you work out the numbers, the precision on the change in L that you can measure with an interferometer like this is this 10 to the minus 8 times the wavelength of the light, 1 micron, divided by a numerical factor that you can calculate from first principles. And what you end up with is a precision in principle of 10 to the minus 15 meters, just from the simple apparatus. That's smaller than the radius of a proton. Now, we have to do better than that in order to measure gravitational waves. And the way you do better than that is, first of all, to use a longer L than 1 meter. We use 4 kilometers instead of 1 meter. That helps. We also use a higher laser power, and we also use multiple laser bounces in the arms. I'll come back to that in a minute or two. First, let me list for you the major interferometers that are coming online worldwide that look for gravitational waves. There's a LIGO project, which I'll be talking about in some detail, which has 3 interferometers, 2 of which are 4 kilometers long, 1 of which is 2 kilometers long. 2 of them are in Hanford, Washington, and 1 is in Livingston, Louisiana. This experiment is in a state of advanced commissioning with sporadic data taking, and we hope later in the year to go into a full-time data taking mode. Another experiment that's quite similar is named Virgo. It's located in Italy, and it has arms that are 3 kilometers long. They're a little bit behind us. They're a couple of years behind us. They're in the early commissioning stages. Another experiment with which we collaborate quite closely is the GEO experiment, which has a 600-meter device in Germany, and they're at a very similar stage to what we are. And then there's an experiment in Japan called TAMA, which has a 300-meter long interferometer. So 3 of these 4 experiments are taking data runs, and we try to arrange our data runs to occur simultaneously so that we could possibly detect something at the same time. So let me go back to the LIGO design. Here's our basic microscope interferometer, a laser coming in here. In our case, we have about 6 watts of light coming out of the laser. It hits the beam splitter here, and the light can go to this end test mass or go through to this end test mass. And the light that comes back from the 2 is recombined and goes to this thing, which is supposed to represent a photodetector, a photodiode. Okay, now, how can we do better? Well, we can make each one of these arms what's known as a Fabry-Perot cavity. By placing another mirror here and another mirror here, we create a resonant optical cavity between these two mirrors. Now, normally, if you don't have resonance, if you just place a mirror right here, all the light would go right back toward the laser, which wouldn't help you. But if you tune the lengths between these two mirrors to be exactly half of a wavelength, half integer number of wavelengths of light, then you do get resonance, and the light will go into the cavity and be magnified. And the fact that it's going to go back and forth many, many times means that during the passage of a gravitational wave, you will have more time to pick up the fact that you're getting shrunken or being stretched. And so the light that comes back out of that Fabry-Perot interferometer has more sensitivity to the gravitational wave because it's had more time to experience that gravitational wave. And we can do still better by putting one more mirror in the system, right here, called the recycling mirror. The idea behind that is that the light that comes back from these two arms and goes back through the beam splitter is wasted if it's just thrown right back at the laser and dumped somewhere. We might as well put a mirror here that reflects that light back into the interferometer and essentially magnifies the intensity of our laser. Okay, so those are the three main techniques that are used to do better than the thought experiment I described a moment ago. Here are aerial shots of the two observatories for LIGO. This is the eastern Washington desert, Rattlesnake Mountain in the background. This is a pine forest in Louisiana, about 30 miles east of Baton Rouge. These two sites are separated by about 3,000 kilometers. It takes light about 10 milliseconds to go between the sites. And so what we would hope is to see an observation of nearly simultaneous signals that are 3,000 kilometers apart. Now, there aren't very many sources on the Earth that could generate that sort of signal simultaneously in both detectors. So that would give us greater confidence that we are seeing something from outer space and not something from the Earth. Okay, here's what the facility looks like in a cutaway artist view. The laser beam passes through a vacuum tube. We want to minimize any scattering of the laser light off of air molecules. That would degrade our measurement. So everything is inside of a vacuum tube. This is one of the arms going off 4 kilometers, the other arm. The optics themselves are contained in these large vacuum chambers, and these can be separated from the main vacuum chamber with gate valves. And this whole setup is protected by a concrete enclosure that looks like a 4-kilometer-long Quonset hut. And you saw that from the air a moment ago. This shows you what the beam tubes look like inside. They're about 1.2 meters in diameter, and this was taken back when they were being baked out. They were heated up to very high temperatures to cause outgassing of the molecules in the beam tube so that we could get a very high vacuum level. The laser is infrared. It's about 1 micron, 1,000 nanometers, 10-watt laser. You can actually buy this, if you have enough money, from a company, Lightwave. Now, on top of what we got from Lightwave, we imposed an elaborate intensity and frequency stabilization system that includes some feedback from the main interferometer, so we have very good stability of our laser, which is important if you're trying to make these sorts of measurements. The mirrors are high-quality fused silica. That's a very high-quality glass. They're about 10 inches in diameter, and they're suspended by a single steel wire, essentially piano wire. And the way that these are controlled is by gluing magnets to 4 points on the mirror and then wrapping coils around those magnets that don't actually touch the magnets. And by running currents in those coils, we can push or pull on those mirrors without directly touching them. So this shows you one of the mirrors here. This shows you a mirror of a smaller type of mirror that's being mounted in a frame. Okay, now I talked a bit about the isolation that you get from a pendulum. We need more isolation than what we get from a pendulum. So the optical tables on which these things are mounted are also themselves on a multi-stage mass and spring system, which behaves very much like a pendulum. Again, if you have a 1 over frequency squared suppression and you have several stages of this, you can actually get tremendous suppression, more than 100 million at the frequencies we care about. Okay, so what are the limitations on what you can measure with one of these interferometers? At very low frequencies, we're limited by seismic noise. These ordinary vibrations in our environment. So right here we have what's called the seismic wall. This plot shows you the strain sensitivity in units of strain per root hertz, strain per square root of hertz. That's an odd sort of unit, but it's actually appropriate when you're dealing with noise processes like what we have to worry about in these detectors. So the strain here is comparable to the sort of strain that we would have from an astrophysical source. So at low frequencies we have our seismic wall, where we have very little sensitivity because we're just being shaken by our environment. In the mid-frequencies around here, we're limited by thermal noise, primarily thermal noise in the wires that hold up those mirrors. And that's something that's irreducible. And finally, at high frequencies, we have what's called shot noise, which is just a measure of the number of photons per unit time that hit our photodiode. That's a fundamental limitation on how well we can measure the intensity. Now, these are the fundamental limits. There are lots of other ways to mess yourself up. There are lots of other ways to have noise in your electronics, noise in the laser, and so on. So the big job of commissioning is to reduce all the other noise sources so that you end up at these fundamental limits. And we're getting close, as I'll show you in a moment. Our best design sensitivity is to get down to a level of 3 times 10 to the minus 23 per root hertz. And with this kind of noise sensitivity, we would be able to hope to see a inspiraling chirp at a level of 10 to the minus 21. Okay, now we have had some problems with these sites. At Hanford, we had a brush fire that swept over the site about 5 years ago. And you would think that would be really bad, but it actually didn't do any damage at all. We had more damage from the fire retardant sprayed on the buildings than we had from the fire. And the reason for that is that there's not much to burn in the desert. So it just swept right through and no big deal. Now, what was a bigger disruption was the Tacoma earthquake back in February 2001. That caused some damage. Some optics were misaligned. Some of the magnets were knocked off the mirrors and so on. So it caused some commissioning delay, but it wasn't that big a deal. Now, something that was even more unexpected than that was this little mishap. This fellow was running along late at night, and for some reason didn't look on his map to find that this thing had been built since the last time he drove down that road. He suffered a minor injury, but more injury to pride, I think.
Before the accident or after?
Now, this did settle, finally, a long-standing dispute about whether you needed to have a concrete enclosure over that beam tube. It's expensive, but clearly it was a wise decision. Now we have a new problem to worry about at Hanford. Mount St. Helens has woken up, and that caused us some problems last fall. We had a lot of microquakes that were interfering with commissioning. We can't sustain too much ground motion, or we can't operate the interferometer. And finally, we had some relief. There was an eruption, and that sort of settled things down after the pressure was relieved inside that volcano. We hope that Mount St. Helens will continue to sleep, but it is a long-term worry. Now, Livingston has had a completely different problem. As I said earlier, Livingston is in a pine forest. Well, pine forests are popular with pulpwood cutters, people who cut down trees to make paper. And so every time they knock out a tree, it causes a little seismic thump that rattles through the ground, and it bothers our interferometers. It turns out we happen to be unusually sensitive to that problem. And it causes us to have about only a 40% lifetime when we tried to operate the detectors for taking science data. The solution to that problem was to retrofit all of our vacuum chambers with what's called an active feed-forward isolation system. Basically, this is a gadget that allows you to sense what's going on the ground, to sense with seismometers and accelerometers the disturbances of the ground, and then to correct for them ahead of time. And it turns out, after installing and commissioning it in last year, it worked. It worked beautifully in our last data run. So we're very happy about that. Okay, let me talk a little bit about LIGO's organization. LIGO Laboratory consists of MIT and Caltech groups, plus the 2 observatories at Hanford and Livingston. And then on top of that, there is a scientific collaboration for analyzing the data and assisting in operations called the LIGO Scientific Collaboration, the LSC. It has foreign partners, and all of this is funded by the U.S. National Science Foundation. Here are the LIGO logos. You'll recognize one of them here, us. Let me show you the members of our group here, aside from myself. We have Dick Gustafson, who's a senior research scientist who spends most of his time out at Hanford. Here he is listening to the cosmos with his headset. He didn't hear anything from gravitational waves, but he seems to enjoy what he's listening to. Here we have 3 of our graduate students. This is Evan Getz, David Chen, and Vladimir Dergachev. Here is research assistant Jennifer Lindell and undergraduate Phil Zapatowski. And we have our group shot here, which has 2 other undergraduates who escaped my camera when I was trying to take single shots. Those are Tim Bodilla and Pete Troyan. Okay, the things that we work on are in 2 categories. We have instrumentation and general support. We work on detector characterization, commissioning and noise reduction, and optical control systems development. But what I want to tell you about today is our work on astrophysical data analysis. We search for periodic sources, namely pulsars. I'll come back to that in a moment, rotating neutron stars. And we've carried out a series of 4 scientific data runs, S for science, S1 to 4. We've had a whole bunch of engineering runs, E1 to E12. You can see that scientists are not very imaginative when they name their data runs. It's not like Operation Desert Storm, it's just engineering run E13. So we've taken these data runs, and we have these sensitivities. our first science run, I'm showing you the best performance from the best interferometer for a given science run. Our first one was in September of 2002. And you can see that on this logarithmic scale, we've come down quite a bit from science run 1 to 2 to 3. And we're getting pretty close to this purple curve, which is our initial LIGO design. Okay, these are the first 3 science runs. I'll show you our 4th science run in a moment. And we've been analyzing that data, looking for gravitational waves. There are many searches that are underway right now. We've looked for in-spiraling neutron star and black hole binaries, the sort of swirling of space I talked about earlier. Well, we've looked for these things, but we haven't found anything yet. We haven't seen anything out as far as Andromeda. But actually, not long from now, we'll be looking out to the Virgo cluster, which has of order 1,000 galaxies to look at, not just a handful of galaxies. So we're hopeful that we'll see something eventually. We've also looked for coincident glitches in all 3 of our interferometers, just something that looks odd that does not look terrestrial in its origin. And nothing has shown up yet. We've also looked for coincident glitches with gamma ray bursts. Gamma ray bursts are these very violent reactions that we think are caused by either in-spiraling neutron stars, in the case of very short-lived gamma ray bursts, or by exploding supermassive stars, in the case of a long-lived gamma ray burst. You may have read in the newspaper about one such event last week. We didn't see it. It was too far away. It was about a gigaparsec away, more than a billion light years away. But if one of those happened a lot closer to us, we'd be able to see it, and we're hoping that that will happen one of these days. We've also looked for a cosmic gravitational wave background that's analogous to the famous cosmic microwave background radiation. We've looked for this, and we haven't found it, but we've been able to set limits on the energy density due to such waves. In the case of gravitational waves, we can set a limit on the energy density that's less than a few percent of the actual energy density of the universe. We hope eventually to reach down to a level of 10 to the minus 6, and with an advanced detector I'll be telling you about later, we may get down to 10 to the minus 10. Okay, we've also looked for pulsars. I'll come back to that in a moment, what the mission group has done. But first, let me talk about known pulsars. We know of 28 pulsars out there that are isolated, not in binary systems, for which we have very well measured radio astronomy signals. So we know exactly how fast they're rotating and any spin downs that they have. We've looked for all of those and have found nothing. That's not surprising because we don't think we have the sensitivity yet to see gravitational waves from those pulsars. But we've carried out that as an exercise to make sure that we can analyze data in that way. The most famous example is a crab pulsar, which rotates at 30 hertz and gives us a signal at 60 hertz. I played for you what that would sound like last time. The crab pulsar is quite interesting because in the near future we'll be able to start quantifying how much of its observed spin down, how much of its spinning down slowly is due to electromagnetic waves and how much of it is due to gravitational waves. So that's for the future. Let me just tell you a little bit about pulsars to remind you. Pulsars are created by the collapse of a star into a neutron star, and the reason they pulse is that they are spinning, and they spin quickly because as the star collapses, it speeds up dramatically. So in that speed up, we end up with a star that is rotating relatively rapidly, and if it has a hot spot like I showed you last time, then you'll see flashes of light that occur periodically. I'm not sure how many of you can see that, but there's a quite dramatic flash as you happen to see in the case of a pulsar, the north magnetic pole or the south magnetic pole of that pulsar. Okay. So these give us very periodic signals, little flashes of intensity that can be radio waves or X-rays. And what we'd like to see is the corresponding gravitational radiation from that spinning process. Thanks, Warren. Okay, now, those are known pulsars. What's more interesting to us here at the Michigan group is to look for unknown pulsars, things that we don't yet know about because they're invisible to us in the electromagnetic spectrum. Now, it seems easy. I mean, after all you need to do is look for a single spike in your audio spectrum, a pure tone. For example, if you had a pulsar rotating at 220 hertz, that would give a gravitational wave signal at 440 hertz, and it would sound something like this. Okay, piece of cake, right? We ought to be able to hear that pretty easily. But there are some problems. The first problem is that the signals are extremely weak. I've talked about signal strengths at the level of 10 to the minus 21 as being just barely observable with these interferometers. Well, these signal strengths are 10 to the minus 24, we think, or smaller. Okay? So we have to observe for many months, if not years, to have any chance of detecting a signal like that. We have to look at it in a very coherent way. Now, what makes that complicated is that on top of the weakness of the signal and the time at which we have to observe it, we have to contend with what are known as Doppler shifts that become quite large for large observing times. So what is a Doppler shift? Let me explain that. Imagine that you have a source of waves. This could be a source of audio waves, sound waves, or it could be a source of light. As it moves in this direction, the waves that it emits get compressed together because as the wavefront is emitted and the object moves a little bit this way, when it emits the next wavefront, the two wavefronts will be closer together than they would have been otherwise. So for someone who's ahead of the source, as it's coming toward them, there is a higher perceived frequency of those waves, whether you're talking about audio waves or light waves. If you're behind the source, oops, went the wrong way, then the wavefronts get spread apart, and that corresponds to a lower frequency. Okay, this is actually a phenomenon you're probably familiar with. Let me, where's our little gadget? Here it is. So here I have a sort of a whistle that will be very annoying for a moment. So bear with me. So you should, as the whistle approaches you, hear a higher frequency, and it comes back toward me, you'll hear a lower frequency. So that's a Doppler effect. And the same sort of thing is happening. Boy, is that annoying. The same sort of thing is happening for neutron stars. If we are moving with respect to the neutron star, if it appears to be approaching us or we're approaching it, its frequency will appear to be higher. If it's moving away from us or we're moving away from it, its frequency will appear to be lower. Now, the effects are actually quite small. What's critical is the relative motion of the pulsars. The size of the effect, the relative change in the frequency, depends on the relative motion of the observer and the source, in this case our motion with respect to a stationary neutron star. And just the fact that the Earth is rotating gives us a frequency change that is of order the rotational speed of the surface of the Earth divided by the speed of light. That turns out to be of order 10 to the minus 6. What's stronger is the frequency modulation due to the Earth's orbital motion. The Earth is moving around the Sun at a fairly high speed, and that gives you a relative frequency change of order 10 to the minus 4. Now, those still sound very small. You would think, well, that's not that big a deal. You should be able to handle that. But let's try some numbers. Let's imagine that we're trying to detect something at 500 hertz, and we're trying to track it over a period of 6 months. It turns out that the resolution in the frequency, the width of what you would call a perfect spike on your audio spectrum, is about 1 over 6 months. So in that case, that turns out to be 63 nanohertz, much smaller than a microhertz. So that's how a perfect spike would show up. The problem is it's not going to be a perfect spike. The Doppler shift is going to be of order 2 times 10 to the minus 4 over that same 6-month period, dominated by the orbital motion of the Earth. So you multiply that 2 times 10 to the minus 4 times the 500 hertz, you end up with a frequency change of about 1/10 of a hertz. And that's huge. That means that our so-called single spike, corresponding to the tone of a perfect pulsar, is not a single spike at all. It's been smeared out over 0.10 hertz over 63 nanohertz, which is 1.6 million frequency bands. So we don't see all of the energy of a pulsar in a single band. We see it smeared out over 1 million bands, which makes it very difficult to detect these things. And unfortunately, every point on the sky has a slightly different Doppler correction. It all depends on the relative motion of the Earth with respect to a fixed point on the sky. And it gets worse. The pulsar could be spinning down. In fact, it's likely to be spinning down. If it's emitting gravitational waves, it must be losing energy. So on top of not being a perfect single tone to begin with, it's actually not perfect. It's slowing down, and we don't know what it is. We're looking for stars that we can't see. So we have to look at a lot of different possibilities. The pulsar may be in a binary system with some other star, in which case there could be very large Doppler shifts that we have no idea what they are. And in addition to that, our sensitivity to a given signal depends on the orientation of our interferometers with respect to that direction on the sky. That is, we get a signal strength that varies as the Earth spins around and as the Earth goes around the Sun. That corresponds to amplitude modulation. It's analogous to using a slowly rotating television or radio antenna. Those of you who are old enough to know what rabbit ears are for a television may recall painful memories of trying to set up a rabbit ear to be just right, so you get a certain television station. Well, imagine how annoying it would be if that thing were just on its own slowly rotating during the course of a day. Well, that's what our gravitational wave interferometers do. Last week I showed you what happens if you detect an electromagnetic wave generated by this gadget here. Here I have an antenna that's connected to a light bulb. There's no power source here other than the electromagnetic energy I pull out of the air from the electromagnetic wave generated by that transmitting antenna. Well, this is what happens if you have your rabbit ears lined up just right, but if they're oriented differently, you don't get a signal. And unfortunately, that's what's happening all the time with our gravitational wave interferometers. We can't stop the Earth from rotating. We can't stop it from going around the sun. So we're stuck with whatever nature throws at us in terms of these antenna pattern modulations. If we had good orientation, if the interferometer arms were aligned with the wave polarization, then we get a nice strong signal. An interferometer aligned in this way would sense this motion quite easily. But if we rotated the interferometer arms by 45 degrees, in fact, we have no sensitivity to this motion at all. Okay? So that's the kind of problem we have to contend with this analysis. And of course, as I said, we don't know where the star is, so we have to, as we search across the sky, we have to keep making these corrections for each point on the sky, and each one is slightly different. But there are some substantial benefits from these modulations, in that if you ever see a signal, despite these difficulties, the reality of the signal will be confirmed by the very need to make those corrections. And in addition, these corrections give us a very precise directionality on the source, okay, because we've had to make all these corrections to know where to find it in the first place. So carrying out a one-year search at the full intrinsic detector sensitivity of LIGO is actually beyond the total computing capacity here on the Earth. We can't do it with the full one-year time resolution that we have in principle. I'll come back to that point in a moment. So what we have to do is use what's known as a hierarchical method. We do a coarse search followed by a finer search for the candidates that appear to be somewhat strong in the coarse search. It means that we're somewhat less sensitive than we could be if we had an infinite number of computers, but it turns out we don't lose that much sensitivity in that process, and it becomes computationally tractable to do it that way. And we have an ongoing search here by two graduate students at the University of Michigan, Vladimir and David Chen, who've been working on this problem for a couple of years now. And I want to show you one plot that Vladimir produced recently that shows you the successful reconstruction of an artificially injected pulsar signal in the data from our third science run. And so this is using this hierarchical search technique where we have a coarse search over the sky, which is indicated by the broadness of this red streak. This is a hot spot of a pulsar whose strength is 10 to the minus 23. Okay, so that's a very tiny signal, but we're able to reconstruct it quite strongly. This is really the first step in a hierarchical search. So we're hoping that we'll have success with this technique, and you should stay tuned. We might see something one of these days. This is what the data looks like from our fourth science run, the so-called S4 run. This shows you again the design curve that we're trying to get to, and this shows you the data from all three interferometers. I'm not showing you here the best interferometer and its best performance. I'm showing you typical performances from all three interferometers. They're all getting very close to their design capabilities. They're within a factor of 2 over a broad spectrum and much closer than a factor of 2 over the sweet spot. Now, it's helpful to keep in mind that there are other interferometers operating in the world. There's the LIGO interferometers I've told you about, the GEO interferometer in Germany, Virgo in Italy, TAMA in Japan. We are hoping that the Australians will put together an instrument in the next several years. If we were able to detect a signal with all of these different interferometers at the same time, not to mention the other bar detectors I've told you about, that would give us much greater confidence that we've actually detected something real from outer space. And also, what is more important, is that it will give us better precision on the source locations and the wave polarizations. The more detectors that see these signals, the more information we have about them. But let me talk about something that we're hoping for the future. The initial LIGO design is somewhat questionable in being able to see something at all. I talked about that last week. We're not sure that we'll be able to see anything with our initial LIGO detectors. The initial LIGO detectors were designed somewhat conservatively, despite all of these technical challenges. They were based on R&D that had been done in the laboratory. So it was essentially putting everything together all at once and making the arms 4 kilometers long. That was what made LIGO special and these other interferometers. And that gave us a sensitivity gain over the previous generation of interferometers of about a factor of 1,000. But it was always envisioned that because of this very low expected rate of detectable events, that we would want to do better in the future. Okay. So in designing and building and commissioning this initial set of interferometers, we've learned how to build an advanced version of the interferometer with great confidence. And we're hoping, in fact, we're actually quite confident, that this next generation, what we call advanced LIGO, will give us a sensitivity improvement of about a factor of 10. Now that helps a lot. LIGO measures gravitational wave amplitude. It doesn't measure energy, the way, say, a photodetector measures energy of light. It's actually measuring amplitude directly. That means if you have an improvement of a factor of 10 in your sensitivity, that means that you can see sources that are a factor of 10 farther away. Not a factor of a square root of 10, which you would have for an inverse square law, but a factor of 10 farther away. Now, if you're sampling the local part of the universe and you can go out farther by a factor of 10, that means you're seeing a volume of the universe that's 1,000 times larger. And if you're looking if you're thinking in terms of event rates per volume of the universe, that means you're increasing your event rate by a factor of 1,000. This is an artist's depiction of that. This is what we might be able to see with the initial version of LIGO. This is what we can see with an advanced LIGO. There's much more to be looked at out there in the universe. So how do we get there? Well, first of all, we need to increase our laser power by roughly a factor of 20, go from 10 watts up to almost 200 watts. That will improve our shot noise, the high frequency noise that's just due to the number of photons per unit time. So that reduces the statistical error. We will use an improved test mass material. We use a fused silica that has a higher mechanical Q, meaning that it rings more like a bell when it's perturbed. That gives us a lower internal thermal noise in the bandwidth that we care about. We'll have an increased test mass itself. We'll go from about 10 kilograms to 40 kilograms. That compensates what's called the radiation pressure noise. So although increasing the laser power decreases the relative fluctuations in the intensity of the light that you see, it causes a different sort of problem. The photons that are hitting the mirror actually carry momentum with them. So as they hit the mirror, they buffet the mirror. And the more photons you have per second, the larger the fluctuations in that momentum transfer of the light onto the mirror, so the mirror vibrates more. So by increasing the mass, we make ourselves less sensitive to that effect. There's more mass, and so if you think back to the term F equals ma, we're increasing mass and therefore decreasing acceleration in response to the same force. We also will use a different suspension systems. Right now we have a single ganowire looped around one of the mirrors. That's our single pendulum suspension system. For advanced LIGO, we'll have a quadruple pendulum system to give ourselves more isolation from our seismic environment. And that will also lower the thermal noise due to the suspension wires themselves. And finally, we'll have improved seismic isolation. The system I talked about that has been installed at the Livingston interferometer to make it less sensitive to logging will also be installed at the Hanford interferometers. That will lower our seismic wall down to something like 10 hertz from the present value of about 40 to 50 hertz. Okay. Now there's another future project that's in the works. It's known as LISA. This stands for Laser Interferometer Space Antenna. It's basically very much like LIGO. You have a laser interferometer. In this case, it's made up of 3 spacecraft that are separated by 5 million kilometers. They will be orbiting the sun in an orbit that's somewhat behind that of the Earth. And by measuring the fringe patterns, the interference patterns that you get from these spacecraft as they send lasers back and forth to each other, you can detect gravitational waves that pass through this region of the solar system. Now this detector is very sensitive to, in fact, it can only see frequencies that are very low. So instead of looking in the 1 hertz up to a few kilohertz band that LIGO tries to do, or 10 hertz up to a few kilohertz, they'll be looking down at the level of millihertz and even smaller because they have these very long arms. Okay. Now, a system like that will be very sensitive to other sources that LIGO will not be able to see here on the Earth. They can look at binaries that are well before their coalescence. They can look at in-spirals of stars into massive black holes like the one at the center of our galaxy. And they can actually look at the coalescence of massive black holes that might be happening somewhere out in the universe. They're virtually guaranteed to see sources, including that Taylor-Holsey binary system I told you about last week that has one pulsar going around a neutron star, something that we cannot hope to see here on the Earth because the frequencies are too low. It's technically challenging, obviously, to put 3 spacecraft up there, align them precisely, and have them talk back and forth to each other with these lasers. But a lot of the R&D has already been completed. It looks quite feasible. And right now, the optimistic launch date would be sometime in 2012, but that depends on what happens at NASA. As you may have read recently, NASA's funding is a bit flaky at the moment because of the siphoning off of funds for the Mars mission. So we're hoping that's not too disruptive. Now, let me mention that there are 2 Michigan scientists participating in this effort, Doug Richstone in the astronomy department and Tim Chupp here in the physics department. Well, let me summarize. the commissioning of the LIGO detectors and these other interferometers worldwide is nearly complete. We are approaching the design sensitivities that were thought to be unprecedented and frankly many skeptics thought would not be possible to achieve. Searches are underway with our early results already reported and more results to come very soon. We have an advanced LIGO project that has been approved by the National Science Board. We now have to get it into the President's budget, but we're hoping that that will happen soon. And that will allow us to start an upgrade in a few years. And that upgrade will increase our expected event rate by more than 1,000. And we also have in the future to look forward to the space-based LISA project that we hope will launch sometime within the next 10 years. So I'm pretty confident that we'll be detecting gravitational waves on a routine basis in the next 5 to 10 years. And hopefully we'll be discovering our first gravitational wave much sooner than that. And that's where you come in. Let me get this guy running over here. And switch displays. You can help find gravitational waves. Actually, before I do that, I just wanted to show you one other slide. I'm sorry. I forgot I had one slide to show over here. So there's a project called Einstein at Home. It's based on the famous SETI at Home project. Basically allows anyone who has a Windows, Macintosh, or Linux computer to help search for pulsars and LIGO data. Your home computer will download a certain amount of LIGO data and look for pulsars in that data. It uses the same software infrastructure that's used in the SETI at Home, search for extraterrestrial intelligence. They're looking in radio signals for signs of intelligence. We're looking in our gravitational wave interferometer data. And so far, this was opened up just a couple of months ago, we have 42,000 users worldwide with 69,000 computers participating so far. And I'd like to think that after this talk, there will be an increase in that number from the Ann Arbor area. You can sign up at this website. I'll show that to you again in a moment. But let me now go over to this. Oops, let's press the wrong thing here. Let me now show you the screensaver. I showed you a snapshot a moment ago. This is the actual, oh, it's not normally that jerky. There's something strange about the computer, but normally it's a little smoother than that. This is showing you the celestial sphere, and you can see some of the more well-known constellations are outlined with these yellow lines. All the magenta spots you see here, and the red ones correspond to known pulsars in our own Milky Way galaxy. And of course, they occupy a band on the celestial sphere. The constellations may look a little bit odd to you because you're looking at them from the outside instead of from the inside. This is projection onto the celestial sphere. And you may try to look for some of the more familiar constellations. If you look closely, it doesn't come out so well on the screen, but you can see a little blue L there, a little green L there, and over here is a little red L. These are the two LIGO interferometers being projected onto the sky. And over here is the geointerferometer being projected onto the sky. The marker that is, oops, that's, my computer is not cooperating. Go back to this full screen view. If you look closely, you'll see a little diamond marker right here. That's telling you where the program is looking right this moment for a pulsar. It's looking at that point in the sky, and down at the bottom it tells you the so-called right ascension and the declination of that point that it's looking at. So those are the coordinates on the celestial sphere. Okay, so this is something you can download. It's actually a very smooth process. You can get up and running in about 10 minutes. And as I said, I hope that you, members of this audience, will sign up in the next 24 hours. Because I told people there's going to be a big surge of activity from Ann Arbor on Einstein Home. So please go to that website. Thank you.
Saturday Morning Physics is sponsored by the University of Michigan Department of Physics and by gifts from friends of the program. Local broadcast is made possible by Pfizer Incorporated.